So I'll just get started.
Ruth, I'm sorry for notification.
There was instruction that I should disable participants annotation. Right. Okay. Okay. So now I have. Oh, sorry. Now my Zoom disappeared. So can you see my slides?
Yes, we can see the screen. Yes.
Somehow something is strange. Somehow this is. Been using Zoom a lot, so I thought. Okay, so I'll just get started now.
Perfect.
Yes, thank you very much for inviting me to speak at the summer school online. I'm an assistant professor at York University in Toronto, Canada. And my research area is actually machine learning theory. And what I would like to do in this, so this mini course is give you a little bit of a taste of what type of questions learning theorists look at some basic techniques, and maybe later in the course also talk a little bit about current research. So more specifically, so this was my plan for the 4 sessions. So today we'll really just do an introduction to learning theory, talk about the basic notions, basic notation, do some warm-up exercises. So actually I'd invite everybody to get ready, maybe have a pen and a paper. Well, actually pretty much in the beginning start with some exercises. And then today also I just want to take you on a small kind of a historical tour of learning theory, talk a little bit about how learning theory has contributed to the development of some of the major machine learning tools. So I think learning theory is really an area where practice and theory kind of influence each other, which makes it a very interesting and exciting research area, I find. So that's the plan for today. Tomorrow, we'll get a little bit more technical. I'll take you through the major, some major techniques. I'll probably talk about VC theory and some other techniques to get generalization bounds. And then on Wednesday, I would like to talk a little bit more about more current research topics. Maybe I'll share a little bit of my research with you. And on Thursday, I understand the plan of the summer school is to have some sort of a fireside chat. So I'll look forward to that. So let's get into the actual topic. So I guess in this summer school, I don't need to motivate machine learning. So I don't need to talk about why machine learning is an exciting research area these days. So I'll talk instead about how we formalize it and how we mathematically analyze it, and what kind of guarantees we can give for machine learning algorithms. And at the very least for today's lecture, I will talk about supervised learning and about binary classification. So what you should have in mind is a binary classification task. So some sort of, you can, have simple example. Maybe you want to decide whether there is a cat in some image or not, or whether some email is spam or not, or whether some image is or some brain scan shows a malignant tumor, or whether it's actually benign, some benign growth, right? So we have a binary classification task. So typically we get training examples of the 2 classes, right? So here the blue and the red points will denote my 2 classes. And what I do is the task is given some data. What we'll do is we'll fit some function, we'll fit some classifier to this data. So here H, you will see, will always denote my predictor. Can you actually see my mouse? Do you see my cursor?
Yes, we see it.
Yeah, okay, good. So H is the predictor. we fit some function, some predictor to the data. And then what is the actual goal? The actual goal is not just to fit some function to the data, but instead, when some new data comes, once we've learned a predictor, comes a new data point, what we really are after is make a correct prediction on this new data point, right? So here comes a new data point whose label we don't know. We don't know whether this email is spam or not, or we don't know whether this tumor is malignant or not. We want this predictor to be so that it gives us a correct annotation for a new unseen data point. So really the question we're after is how well will H predict on new unseen data points? This is somehow what the whole story of supervised learning is about. So now I'll take you through the formalism. A little bit of a warning, the next slide will have lots of notation. I'd probably encourage you, once the slide is fully built up, to maybe take a screenshot just so that you have the notation ready for the rest of the talk. So here's how we formalize this supervised learning setup. So our data points, right? So we can have this binary classification picture in mind. The data points, they live in some feature space. So X will always be some feature space. The feature space, and typically this is some sort of a lower, depending on the task, lower high dimensional Euclidean space. Maybe we took some measurements. Maybe this feature space represents some images, right? So the feature space, the instances live in some sort of Euclidean space, we'll assume for this lecture. And the label set in a binary classification task is just two different labels, say positive or negative outcome, 0 or 1, +1, -1. And then the input to a learning algorithm is a data set, right? So we have a data set that is just a sequence of feature vectors with labels. So we assume that the learner gets annotated data as input, and the predictor is just any function from the feature space to the label space. So it's just a function from this Euclidean space to, in this case, 0 or 1. Right, and the question is, how do we actually measure how well a predictor does? So typically we measure this, or in order to measure this, we need to specify a loss function, right? And in binary classification, the most natural loss function is just a binary loss function. So here, so L will always denote my loss function. Loss function is always a function that takes in a predictor and an input and an output. Right, so it takes in a predictor, an input and output, and we want to decide the loss function should somehow measure how well is this predictor doing on this input-output pair. So in binary classification, really what we're asking is just, is this predictor giving me the correct classification on this example or not? Right, is H of X actually, does it correspond to the label that was observed in this, the true label of this example? So this is what we call the binary loss function. If you have a regression task, then you probably want to use a different, then you want to have a loss function that somehow measures how far is the predicted output from the true output, from the true target. So loss function is a function that measures how well we're doing. And then once we've specified the loss function, we have a data set, what we can always compute is an empirical risk, right? So the empirical risk is just we're averaging this loss function over our data set, right? So I'm just, if I have some data set, my predictor, maybe I have 100 data points, my predictor makes 3 mistakes, so I'm counting 3 over 100, normalized by the size of the data set. This is going to be my empirical risk. But now, as we already said in the previous slide, we're not really just after having a low empirical risk. We want to actually do well on new unseen data points. And since we don't know what the actual process is that is generating the data, if we knew exactly what the process was that is generating the data, we didn't need to do any learning. There would be no need for machine learning. So the unknown quantity in this whole setup is the data generating process. And how do we mathematically, we model this uncertainty, the unknown, we model it as a distribution. So we say the data generation is a distribution over the product space, the input times the output. So this distribution actually generates these type of examples. Right? So this is kind of a modeling of what is uncertain in this whole setup. So we say the data generation, we model it by a probability distribution. And then the basic assumption that is behind most of most of the approaches is that our data is an IID sample from this distribution. And the learning algorithm then is an algorithm. And here, for now, we'll just think of this algorithm again as a function. It's just a function that takes in a data set and outputs a predictor. Right? So learning algorithm takes in as a function. Really, afterwards, we'll actually also want to think about, is this an algorithm? Is this an efficient algorithm? But for now, we just think of it as a function that takes in a data point, outputs a predictor. And then the goal, now we can formally phrase our goal. The goal of a supervised learning setup is to say we want to find a predictor H, that is the output of our learning algorithm on the data set. So A of S, learning algorithm, gets the data set as input, outputs a predictor, and we want this predictor to have a small true error, or the true loss. And what is a true loss? Well, the true loss is the expected loss over our data generating distribution. Right? So whenever we have a loss function and we model our data generating process as a distribution, we can say, well, our goal really is to get a small expected loss. Right? And if you have a binary classification task, you can also think of this expectation. This loss function is binary, just take 0, 1 values. This is actually the same as, say you draw a new data sample from your distribution. What's the probability that this predictor, that this classifier misclassifies this input output pair? Right? So this is what we want, that the probability that a new point is misclassified is actually small. So this is the slide that I would recommend maybe take a screenshot, just so that you know what notation I'm using. Right, so I'll just wait half a second. So everybody feel free to take a screenshot or take a picture so that you have this notational setup ready. Okay, so now the challenge is actually that we don't know what the true data generating distribution is. We only get to see the data set. We can compute an empirical loss, and really what we're interested in is, how close is the empirical loss that we compute? How close is that to the actual true loss? Right. So now I'll get to the first quiz already. So everybody has this notation hopefully recorded in some form. So here's the first quiz. So I'll claim that given any predictor, so I can take any classifier. So it's from my feature space to 0, 1. We're in a binary classification setup. N is my sample size, so I have so and so many data points. Then I'm claiming for every data generating distribution P, so no matter what the data generating process, the expectation over the empirical loss is the true loss. So in my quiz is now, let me show you the quiz. So what I'm asking you, is this true for any fixed sample size N? Is it not in general true for fixed sample size N? C, is it maybe only true for large enough N, and that N should depend on P? Should it be true for large enough N depending on H, on my predictor, or is it only true in the limit? I could also maybe, this expectation will converge to the true loss, but it's not, it's never actually equal. So I don't know. Can you do the quiz? Can we do a poll? What do people think?
It's now live, so participants can just have to click. They just have to click the link on the Zoom chat, and they will be taken to the poll with the options.
So do I have the chat here? Actually, I don't see the chat.
The link is already in the chat, and they will be
so now I go to this link.
So we are getting answers on the poll.
Okay.
So this is changing. So there is a clear winner so far. So we'll wait a bit to share the answer.
Okay. So I'm not actually inside the.
So
so I'll just wait a moment, let everybody think. Maybe yes. Once you see some trend, let's see what.
Well, already on the chat box, we have a very clear trend.
Okay.
Also on the poll, on the poll, the option number E is by far the number one with 80%. Number
Okay.
A is 20%, and all the others 0%.
Okay. Which one is 20%?
A.
A. Okay, so we have kind of bimodal. Some people think A, many people think E, nobody thinks B, C, or D.
Yes.
So that's interesting. So let me show the answer actually to this quiz. So my claim was that for any distribution, the expectation of the empirical loss is the true loss. And the answer is this is actually true for every fixed sample size n. And so it's interesting to see the result of the poll is somehow what I would have expected. So the tendency, of course, is to say, well, we first need to see enough data, and then maybe once the data set is large enough, we get a good estimate of the true loss. But here, actually, if we just look at a function, we look at a fixed function and we look at, what is the expectation, even if I just draw one sample point, this is actually exactly the true loss. So even if I have just sample size 1, very small sample size, the expectation of the empirical loss is actually the true loss. And we can also just quickly go through this mathematically. So if we wanted to calculate, if we want to clarify to ourselves why this is formally correct. So here I'm just writing out now the expectation of the empirical loss, right? So this expectation, this is how I define the empirical loss. So the empirical loss is I average over my data set size, how many mistakes did I make? Now, the one thing you need to remember here, if we want to do this little calculation, is that an expectation is always a linear operation, right? So expectation is a linear operator. So what that means is that I can take this constant here, the 1 over n, I can take it out of the expectation, and also the sum, I can take it out of the expectation, right? So since an expectation is a linear operation, I can take this out, and I'll get actually an average over this expectation. And now, so here from 1 to n times, I'm now sampling a size of n, a sample set of size n, but I'm only looking at the ith data point in this sample. So really, I don't need to sample a full set of size n here, right? I can just sample 1 point. So this is the same as just sampling, averaging 1 over n, sampling 1 point. Am I making a mistake on this 1 point? And this is actually exactly how we define the true loss, right? So now I'm n times, I'm summing up the true loss, and then I'm dividing by n, so I'm actually getting exactly the true loss, right? So this is a very good thing to remember, right? So the expectation, on expectation, we see the correct thing. We are after a function that has a small true loss. On expectation, we see the correct thing even on small data samples. So now let me make a new claim. So this is the second quiz. So now I'm claiming, so let n be some sample size. We just got optimistic. We said, okay, for any sample size, if I draw data from my distribution on expectation, I see the true loss. So now, again, let n be any sample size. Then for all learning algorithms, I'm claiming, and for all distribution, the expectation of the empirical loss of the output of my learning algorithm is the true loss. So what about this one? So I'm giving you the 5 options. Is this also true for any fixed sample size n? Is this not true for any n actually? Is this true for large enough n depending on the distribution P? Is it true for large enough n depending on A? Or only in the limit as n goes to infinity? So I guess we can do a quick, I'll let you think about this one a little bit, and we can do the quick poll.
Yes, the poll is live on Slido, so people can already start voting.
Okay. So I'll just wait for,
yes,
once we see some trend, let everybody think a little bit. So do we see any?
We are starting to get the answer, so people are still voting,
Okay.
changing. So we have, with 40% of the respondents, answer E as the number one.
Mm-hmm.
In place number 2 is answer A with 30%.
Mm-hmm.
And we have B, 13%, and then C and D with 6%. So it is in E and A. Now A has been growing as well. So it's,
right. So people got more confident in A, but it looks very similar, but it's a little bit more mixed. Right. So this statement actually it looks very similar to the statement before, and one could of course then be tempted to go for the same answer A. But I guess as students, you could guess that if the answer was the same, maybe I wouldn't have asked the same question. So let's resolve this quiz. So here my claim is for any learning algorithm for any distribution on expectation over the empirical laws, I will see the true loss. Right. So this is actually as stated like this. It's not true for any sample size n. So this statement as a whole is not true for any sample size n. So if we now look back at the question, so I'll resolve this quiz in a moment. Of course, here one could have actually answers n depends on the learning algorithm or on the distribution. This could also have been correct to some degree, but if I take the statement as a whole here, for any algorithm, for any distribution, the expectation of the true law, expectation of the empirical loss of the algorithm's output is a true loss, then this is actually not true for any sample size n. So let me just give you a small proof and convince you why this is not correct. So what I'll show you is that there exists. So if I want to negate this statement for any learning algorithm for any distribution, I will need to show you there exists a learning algorithm and there exists a distribution such that this thing is not true. So I'll show you an even stronger statement. I'll show you that there exists a learning algorithm and a distribution such that for any sample from this distribution, the true loss will always be 1 and the empirical loss will always be 0. So I'll design a learning algorithm that on this particular distribution does really poorly in the sense that it has a very small empirical loss, but a very large true loss. Right, so that's very different from what we saw before. So let me just take you through this small construction here. So I'll design a distribution and learning algorithm as follows. So I just look at, say, a 2-dimensional feature space. So my feature space, say, minus features taking values in -1, 1. I have 2 features. I look at a distribution that is uniform over this feature space and always produces examples with labels 1, right? So I could think of, I don't know, maybe I have to do like a small surgery, and I look at some hospital's record on this small surgery, and depending on, I don't know, the say the time of the day and the experience of the surgeon, actually the surgery is such a simple surgery, it always goes well, right? There's always positive outcome. But my learning algorithm, so what this actually means, so if the distribution always produces positive examples, then any sample from this distribution will look as follows, right? So I see some feature vectors and always with a positive label 1. So it's actually a really nice world that we're living in here. But my learning algorithm is very pessimistic. My learning algorithm does the following. The learning algorithm, so remember A of S is a predictor, right? The learning algorithm takes in an sample S and outputs some predictor. So we can apply this predictor to a new feature vector X. So now this learning algorithm says, well, okay, if I saw the sample, this particular point, I saw it already in the sample, I'll agree. I've seen it with a positive label. I've seen the surgery on this particular patient went well. Okay, I agree, this is a positive. But any other case, I'll keep pessimistic. I don't believe. I'm very scared of my surgery, so I'll just keep believing that all other cases is going to have a negative outcome, right? So this learning algorithm, it does perfectly well on the sample, right? It does perfectly well on the sample. As soon as it saw some data point in the sample, it will admit that this was a positive example, but everywhere else, it'll keep believing the label is 0, it's a negative case. Right, so now we have that the empirical loss of this, the outcome of this learner will always be 0, just by design. But the true loss I'm claiming is actually 1. Why is this? So I don't know if we can allow people to put something in the chat or say a few words. So can anybody tell me why in this case, the true loss of this predictor that the algorithm output on this distribution, why is the loss 1? So the predictor says 1 on the points that it saw in the sample. Everywhere else it says 0. Anybody has an idea? I don't know if I can open the chat. Right. So somebody says measure offset is 0. Why? So let's go back to this example. I mean, this is a correct answer, right? So the point here is that I have a uniform distribution over this uncountable space, and any finite, a sample is always finite. So this predictor is correct only on a finite number of points, but on all the rest of the domain, the predictor is still incorrect, right? So a finite number of points in a uncountable space, distribution over an uncountable space has measure 0. Therefore, the true loss of the output of this algorithm will be 1. So this algorithm actually does really poorly. It gets 0 mistakes on the sample, but full loss 1 on the actual distribution. So what did we see so far? So we saw, in quiz 1, I'm claiming for any age, for any sample size, and for any distribution, the expectation of the empirical loss is actually the true loss. And now in quiz 1, I said, well, there exists a learner and there exists a distribution such that no matter what the sample size, the empirical loss and the true loss will be really far from each other. So the empirical loss of the predictor that I see on this data set for this learning algorithm is not a good indicator of what its true loss is at all. So now my question would be, is there a contradiction? So what is the difference between these two setups? So why can they both be true, or did I cheat you somewhere? Anybody has any? So I see somebody said something on the chat. Right, so this was still to my previous question. No matter how many sample points you sample, there's always an infinite number, an uncountably infinite number of points that I don't sample. That is correct. So what is now going on in this situation here? So why aren't these two statements contradicting each other? And if not, why not? Where's the difference? What's the crucial difference here between these two setups? Why is in this case the empirical loss seems to be a good indicator of the true loss, but in this case, it's not a good indicator I made. This is kind of a standard tool. So how are we going to use this? So we want to show that the true loss of my empirical risk minimizer is bounded by the true loss of the best in the class plus this term, right? So let's see, how can we get a bound here? So first thing I do is I just bring this true loss of H star, I bring it to the other side. So I'll just want to bound this difference, right? The true loss of my empirical risk minimizer minus the true loss of H star. So how can I bound this? The first thing I do is I subtract the empirical loss of the empirical risk minimizer plus and add the empirical loss of H star. So, and here I'm claiming now I only made the expression larger. Can anybody in the chat tell me why is this step correct? I don't know if somebody is still, let's see if anybody's still awake.
We are.
You are awake. Any idea on why this is correct? Or I'll just wait like very shortly. Triangles inequality is actually even simpler. It's very simple. So I was subtracting something and I was adding someone. introducing 0. It's not 0. So I'm claiming here it could be potentially larger than 0. Why? But why is it always larger than 0? So I'm what I added here is always larger than 0, I'm claiming. So by definition of H star, exactly, yeah, that's half the answer. So by definition, H star is the best from the class, exactly, H star is the best from the class, but with respect to the true loss. So H star is best in the class with respect to true loss. So what I also need here actually, so maybe I'll just move on now, but this is half the answer. So it's by the definition of H star and H hat. H star is the best, is a function in the class that has the best true loss, but H hat is the function that has smallest empirical loss. So I'm subtracting something, but then I'm adding something larger. So H star always has at least as much empirical loss as H hat, because by definition, H hat is the empirical risk minimizer. Right, so here I only made this expression larger. Now, and now it gets very simple. So now what I'll do is I'll add some absolute values. So let's see here. So I just took the same expression, added absolute values here. So again, I made things only larger. And now I'm saying, well, now I have twice this, I mean, I have this expression here, empirical difference between empirical and true loss. I mean, this is the quantity you'll realize that I'm kind of obsessed with in this lecture, right? What is the difference between the empirical and the true loss, right? So here of H star, here again, difference between empirical and true loss. Oh, here's the P is missing. Difference between empirical and true loss of H star. So I can bound this by 2 times the largest possible difference in my class H between empirical and true loss, right? So now what this shows me is that if I can bound this quantity, if I can somehow for all functions at the same time bound the difference between the empirical and the true loss, then I get a bound on this quantity, and then I get the error bound that I was claiming at the beginning. Right, so this is actually, so maybe let me just mention this term. This is what's called uniform convergence. If we can uniformly, for all functions in the class H, we bound the difference between the true loss and the empirical loss. And then we have what we call uniform convergence. And that will get us the result that we're after. So now to prove this uniform convergence here, we'll use Hoeffding's inequality. So we'll fix the function h first now. We fix the function h, and we'll set our random variable is, what is the mistake that h makes on a data point, right? So I have n instances of this random variable. So that did I make a mistake? Did h make a mistake or not? So if we now plug this in, so this was the expression we saw in Hoeffding's inequality. So now in the language of a classifier that makes mistakes, this translates directly to the difference between the empirical loss and the true loss. So what is the probability that this is larger than epsilon? Well, now we can bound this. With this expression from Hoeffding's inequality. It goes exponentially down with the number of data points that I saw in my sample. So this is more like the situation in quiz 1, right? So in quiz 1, we were just talking about one function, right? So for one fixed function, we can bound the difference between the true and the empirical loss simply with Hoeffding's inequality. We actually want to do this for all functions in our class. But since our class was finite, this is now also simple. So this was the quantity we wanted to bound, right? The true loss of the empirical risk minimizer minus the true loss of the best function in the class. We saw that it's bounded by 2 times the sup over the class. So here we can say, well, this is larger than epsilon only if the maximum difference that we observe in the class is at least epsilon over 2. So this is equivalent to saying, well, when is the maximum over my class larger than epsilon 2? Well, when there exists at least one function in my class for which it's larger than epsilon 2. So either for the first function in my class, true loss minus empirical loss is larger than epsilon over 2, or for the second function in my class, true minus empirical loss is larger than epsilon over 2, or for the third, and so on. So I have this big or expression here. So now I can remember my basic probability theory, and I know that in OR of events, I can use the union bound and turn this into a sum of these, the probability of these each of these events, right? So for every function, this is actually the same probability, and we bounded this with Hoeffding's inequality. So I get the size of my class times this expression from Hoeffding's inequality. And now it's really just a little bit of calculation. I set this to be my my confidence parameter delta. I solve for epsilon, and then I'll actually get exactly the type of statement that I wanted. Right, so the probability that the true loss of my empirical risk minimizer minus the true loss of the best function in the class is larger than this expression. This is my epsilon now, is bounded by delta. So now I showed you, and I realize I'm out of time. So this is the theorem that I showed you. So I showed you now that finite classes are packed learnable. So maybe I'll take a break for questions. Maybe I move the historic tour to tomorrow, or what is the?
Well, maybe there are questions from the audience. Otherwise, we can so stop it here and then continue tomorrow.
Yeah. So if there's any questions, so I'll wait a bit if there are any questions. No question. Maybe I overwhelmed everybody, or it was too easy.
The comment is rather a compliment. So yes, it was a very nice introduction, and I would say that tomorrow we can continue with the next part.
Yeah. So we could also, if you wanted to collect questions and send them to me, I could, answer them in the beginning of tomorrow.
Well, the idea is that exactly, so in the Fireside chat, it will be question and answers only. So people can write in advance their questions, and then we will cover them in that slot.
Okay. Yeah. Okay. So I'll end here for today. I'll go over the historic tour tomorrow in the beginning, and then we'll see a bit more of classic learning theory. And then on Wednesday, I'll tell you some more recent research topics. Actually, that's the plan.
There's actually one question, Ruth. So last minute. So it says 3 slides ago, why there is this absolute L? So
3 slides ago. Which one was 3 slides ago? This one?
Absolute. The supremum.
This one here? I don't know if we can allow the
yes, that one.
This one. Right, so here actually, I mean, if I just look at the line before, right, I have true loss minus empirical loss for some H star is some of one of the functions in my class. And here, H star is another function. Here's a P is missing. I have to fix this, right? So, but again, it's the expression is true loss minus empirical loss, right? What's the absolute value of this? So this is, both of these are definitely bounded. Both of these summands here are bounded by the largest possible in my class. So this could actually be a max because my class is finite, so it doesn't need to be supremum. Here I'm actually assuming my class is finite. So this can be the maximum. So the maximum difference between true and empirical loss over my class is definitely going to be larger than each of these two. Right, so the sum of these two is at most 2 times the maximum of the difference between empirical and true loss in my class. Did that answer the question?
Yes, the person writes that he did. So thanks.
Okay, good. Okay, great. Okay, so I guess I'll see you tomorrow, my morning and your afternoon.
Yes, so it will be in evening. And thank you very much, Ruth. And let's continue tomorrow.
Yeah, thank you.
We will move now to our poster session, so we still have a bit of activities left in the day.
Okay.
But thank you very much, and we'll continue.
Yeah, great. Thanks a lot.
Have a nice day.
Yeah, you too. Have a nice evening.
Yes. Bye.